because if we round the polytope, then this makes it much easier to generate samples from the uniform distribution on the polytope. And another reason is that it also makes it much easier to compute the volume. So specifically in the setting where the number of inequalities m is greater than or equal to the dimension n cubed, the current bottleneck in computing the volume of polytope is actually this pre-processing step where one rounds the polytope and brings it into isotropic position. OK, so there's a long line of work on the problem of computing the volume of a polytope. So generally, what one does is to compute the polytope volume is that one generates samples from the uniform distribution on the polytope, and this then allows one to compute the volume of the polytope in polynomial time. So typically, these samples are generated by running a Markov chain on the interior of the polytope or on a sequence of polytopes, where the last polytope in the sequence is the polytope k, whose volume we want to compute. OK, so here we have Markov chains, various Markov chains appearing in recent works. And some of these Markov chains give imply the best current bounds for computing a polytope's volume in different regimes. So we also have here the number of arithmetic operations, sort of in the first column, that these Markov chains require in order to compute the volume of polytope. So the number of arithmetic operations depends on two things. So it depends, first of all, on the number of Markov chains the number of Markov chain steps that the Markov chain requires to compute the polytope volume. And it also depends on the number of arithmetic operations that we require to implement each individual step of the Markov chain. So most past work has focused on reducing the number of Markov chain steps required to compute the polytope volume. So in this talk, we're instead going to consider the problem of reducing the number of operations required to implement each individual step of the Markov chain, so the number of operations per step. And specifically, we would like to obtain a Markov chain where the number of operations per step, so we would like to reduce the number of operations per step for the ball walk Markov chain so that it's so that it's sublinear in the input size of the problem, which is the number of inequalities m times the dimension n. So all the current Markov chains, which can be used to sample from a polytope, currently require a number of operations, which is at least linear in m times n to compute each step of the Markov chain. So we would like to reduce this so that it's sublinear in m times n. And we're going to do this for the ball walk Markov chain. OK, so now I'll talk a bit about our results. So we show that when sampling from a polytope in isotropic position, we can implement the ball walk Markov chains in roughly m operations per Markov chain step on average. So this is sublinear in the input size m times n. So we then show that this result implies a cost of m times n to the 4.5 arithmetic operations to round the polytope, to bring it into isotropic position. And it also implies the same m times n to 4.5 arithmetic operations to compute the polytope volume. So this improves on the previous best bound for rounding a polytope by a factor of square root of n. So we get this improvement in the regime where the number of inequalities m is greater than or equal to the dimension n cubed. And since the rounding preprocessing step is currently the bottleneck for volume computation in this regime, we also get an improvement of square root of n for computing the volume, for the number of arithmetic operations it takes to compute the volume of a polytope. OK, so this is a more formal statement of our result. OK, so our algorithm is based on the ball walk Markov chain. So the ball walk is a Markov chain on the interior of polytope. So at each point in the Markov chain to compute the next point of the Markov chain, the ball walk proposes a step which is uniformly distributed on a ball of radius 1 over root n, centered at the current Markov chain point. So if this proposed step satisfies all m inequalities that define the polytope, then the ball walk moves to this step, and otherwise, if not, then it proposes a different random step. So this means that in order to compute each step of the ball walk Markov chain, we have to check m inequalities. So the question is, how can we avoid computing all m inequalities at each step of the ball walk? So to solve this problem, we introduce a sublinear implementation of the ball walk Markov chain. So the way this our implementation works is, first of all, at the first, so the initial point x1 of the ball walk Markov chain, we compute the distance to each face of the polytope, so to each hyperplane defining a face of the polytope. So we compute this distance delta I to each hyperplane hi of the polytope, and we then rate roughly delta I times n ball walk steps before checking the distance to the hyperplane hi again. So the idea is that at each step of the ball walk Markov chain, we only compute a very small subset of the distances to each of the hyperplanes. So this allows us to implement each step of the ball walk in a much smaller number of arithmetic operations. Okay, so the first question is, why does this implementation of the ball walk actually work? So why does the ball walk not leave the polytope, since we're only checking a small subset of the inequalities? So to prove that the ball walk doesn't fail, this implementation of the ball walk doesn't fail with high probability, we can see that at each step of the ball walk Markov chain, so each step is uniformly distributed in a ball of radius roughly 1 over root n. So this implies that the ball walk travels at most a distance of roughly 1 over n in the direction of any given hyperplane defining a polytope face at each step of the ball walk Markov chain. So this implies that with very high probability, if we use if we weight roughly delta I, where delta I is the distance that we computed to the hyperplane, times n ball walk steps before recomputing that distance, then our ball walk will not leave the polytope for a very long time with high probability. So more specifically, if we want our ball walk to not fail for a very large number t of steps, then we need to wait a time of roughly delta I times n divided by log of t. Okay, so this shows that our algorithm doesn't fail with high probability, and it also shows that our algorithm will follow the exact same steps as the original ball walk algorithm for a very long time. Okay, so far we've shown that our algorithm succeeds in implementing the ball walk, but we still need to show that it implements it faster. So we want to show that it implements it faster by a factor of n. So to do that, we want to bound the expected waiting time, this delta I times n, and show that this quantity is, on average, is greater than or equal to roughly n. Okay, so we only know how to bound the expected, we will only bound the expected waiting time when the polytope is in isotropic position. So to allow us to round the polytope by sampling only from isotropic polytopes, so isotropic convex bodies that are very close to polytope in some sense, we consider a sequence of roughly n polytope-like convex bodies. So each convex body in the sequence can be transformed into isotropic position by computing roughly n samples from the previous convex body in the sequence. So this construction allows us to round the polytope by sampling only from isotropic convex bodies. So it also allows us to initialize, so this same construction also allows us to initialize our Markov chain at roughly a uniform random point inside each of these convex bodies. Okay, so how do we bound the running time of the total running time of the algorithm? So our algorithm, so there's roughly n convex bodies inside this sequence, and we generate n independent samples from each of these convex bodies. So that's n squared independent samples in total. So we also will show that the expected cost of each step of the ball walk is roughly equal to the number m of faces of the polytope. And finally, we also know that the ball walk mixes in roughly n to the 2.5 steps on an isotropic convex body. So that's a recent result by Lee and Vipala. So putting these three facts together, we get that our algorithm takes roughly m times n to the 4.5 arithmetic operations to round the polytope, so to bring it into isotropic position. Okay, so we still need to do one more thing. So we still need to bound the expected, so in order to bound this expected cost of each ball walk step, we need to bound the expected waiting time, which is this distance delta I. We compute to each hyperplane times n. So this is the expected waiting time until we compute the hyperplane again. So how do we do that? Okay, so to do that, we show this anti-concentration lemma. So basically what this lemma says is that if we have a point x that's uniformly distributed inside our polytope, and the polytope is roughly in isotropic position, then the distance between, if we look at the distance between this point and any face of the polytope, any hyperplane defining face of the polytope, then the probability that this distance is less than or equal to some number epsilon, so that probability is bounded above by roughly epsilon. So in other words, what this is saying is that if we look at this red strip, this red region, consisting of all the points that are a distance at most epsilon from this any given face hi, any given face of the polytope, then the volume of this region is a fraction of at most epsilon of the total volume of the polytope. So this is an anti-concentration lemma. Okay, so how does this lemma help us? So since our construction allows us to start the ball walk in a uniform, at a roughly uniform random point, so a warm start, and our polytope is roughly in isotropic position at each point in this construction, then the anti-concentration lemma implies that the expected distance to each face of the polytope at every step of the ball walk is roughly equal to something on the order of 1. So this implies that the expected waiting time until we compute this hyperplane again is the expectation of delta I times n, which is roughly equal to n. Okay, so basically we've shown that on average, we only need to compute each inequality of the distance to each hyperplane of the polytope once every n steps of the ball walk. So in other words, this means that on average we get an improvement of roughly n, a factor of n on the number of arithmetic operations needed to implement each step of the ball walk. Okay, so now I'll talk a bit about some future directions. So basically, so far we've shown how to improve the per step complexity of the ball walk from m times n to just m arithmetic operations, so improvement by a factor of n in the context of polytope rounding and volume computation. So this improves on the previous best bounds for both polytope rounding and volume computation by a factor of square root of n to m times n to the 4.5 arithmetic operations. So the first question that we have is, can we make further improvements to the per step complexity of the ball walk? So specifically, we conjecture that the per step complexity of the ball walk can be brought down to something on the order of log of m, so logarithmic in the number of polytope faces. And the second question that we have is, can one improve the per step complexity of other Markov chains used to sample from polytopes, which may mix in fewer steps in many settings than the ball walk? So specifically, Riemannian HMC, hidden one, Markov chain or the Dijksenwalk. For hit and run, okay, so I'm not sure how to do it for hit and run. So it would be nice if you could do it for a hit and run, but the problem was so with hit and run, in some steps you might go a very long distance. So right, but it's definitely an interesting question. Okay, so basically, so the reason it's true, so it's not, so the proof is fairly simple. So the way this works is that, at least the sketch of the proof, so the way this works is that since the polytope is in isotropic position, the uniform distribution on the polytope so this is a log concave distribution, and it has covariance matrix roughly 1. So we're interested in the distance from any point from this uniform distribution, x, and of just any hyperplane. So we can just consider any hyperplane. It doesn't need to be a face of the polytope. And if we look at the distance, then in some sense, since it's a log concave distribution and it has covariance 1, we can project it onto the direction, the direction to the hyperplane, the closest line to the smallest distance, the direction of the smallest distance to the hyperplane. And so if we project this log concave distribution, so whenever you project the log concave distribution onto a subspace, then you also get a log concave distribution. So the projection of the distribution is also, the marginal distribution is still log concave. And so now you have a one-dimensional log concave distribution, which has variance 1. So you can use that to then show this anti-concentration result in the one-dimensional case. That's basically the idea. Thank you.